Hello, my name is Daovili.
I'm Liu.
We are from Zhejiang University. Here we present our research on personalized highway pilot assist, considering leading vehicle behaviors. Highly automated driving has attracted much attention around the world. Analysis, for example ABS, FCW, ACC, has also made great progresses since 2000. The penetration rate of Level 2 automation rises quickly even in entry-level passenger cars. Recently, highway driving automation has become the front line of the competition. In premium segments, hands-free driving function is very popular, but still there are many issues remain to be studied. For ADAS products, driver acceptance is important for safety and comfort, but survey shows that the acceptance of current ADAS products is very low. When developing ADAS products, we need to consider drivers' characteristics. In a longitudinal direction, there are many car-following models since the 1950s. Related ADAS developments mainly focus on longitudinal direction. There's no enough consideration of lateral movements. In the lateral direction, for example, lane keeping, usually the lane center line is chosen as the desired path. There are just a few studies on driver's own lane center or some personalization studies. So we need a better personalization methodology for highway pilot development. We need to consider interior coupling between longitudinal and lateral driving tasks. We also need to consider drivers' preferences in highway driving. In this study, we use the framework as shown in this figure. First, we use high-D dataset and simulated experiments to understand driver characteristics in highway driving. Based on this understanding, we applied to design the personalized highway pilot algorithm in this red block. During our previous research on car-following model, we accidentally found that there is a follow-shoot phenomenon in car following on highway. That is, some drivers are likely to be affected by the leading vehicle's lateral movement. Based on a high-D data file, we found 664 follower-leader combination cases in total. This video shows an example of such follower-leader combination case. When the leader vehicle moves to left or right, the follower vehicle will also move left or right in a period of time. The statistics show that there are over 40% of affected cases in more than 600 follower-leader combination cases. This phenomenon is observed again in simulated driving, vehicle trajectory similarity analysis, and also driver's gaze behavior are used to analyze such preferences. Based on these results, we speculate that first, in car-following scenario, subjects pay more attention to the leading vehicle than that in free driving. Drivers may handle lane-keeping tasks by mainly referring to the leading vehicle, no matter whether they are aware of it or not. Second, all subjects are affected by the leading vehicle, at least 10%. It means that this is a very common phenomenon in car following. Therefore, lateral movement in car following is actually a representation of driver style. It should be considered in the highway pilot development. With this inspiration, we propose a personalized highway pilot algorithm. Based on the manual driving data, we first get the driver preferences. That is, we use the trajectory, the eye movement data to get the driver preferences. And then we have the personalization data. For the personalized vehicle motion control, we include speed control and also lane keeping model. For personalized speed control, we use IDM and adapting the parameters. For the personalized lane keeping, we use the stimulus response model. That is, we use the lateral movement of leading vehicle as a stimulus, and then we have the eagle vehicle's lateral movement as a response. This equation schemes the stimulus response model of personalization. That is, we use alpha to indicate the preferred sensitivity to the stimulus, and we use tau to indicate the response time. That is, how quickly the follower driver will respond to the leading vehicle's lateral movement. Therefore, we have the automated driving with personalization.
We conduct an experiment to validate our algorithm. The 16 subjects are invited again, equipped with a wireless ECG sensor, and the physiological signal is collected by biopack device and recorded by supporting software. They are asked to sit in the cockpit of driving simulator and to concentrate on the car-following driving process. The proposed algorithm and two comparison algorithms are tested. The validation results are shown here. We choose two metrics, the R interval and the LF-HF ratio, to measure the driver mental workload during following driving. We can see that the R intervals in our proposed algorithm P are generally higher than which in comparisons C1 and C2. On the contrary, the LF-HF ratios in P are lower than which in comparisons. The performance of both metrics shows that our personalized algorithm brings a lower driver mental workload in highway following driving.
To conclude, we report findings on how drivers' lateral driving maneuver is affected by the leading vehicle behaviors. We then apply this understanding to the design of personalized highway pilot. Simulated experiments and evaluation results show that it can reduce driver mental workload significantly. It can also improve driver acceptance. This study may serve as a foundation in future ADAS development and implementation. Thank you for watching.